Hey guys, in this week's lecture, we're going to talk about 4.7 in the textbook, L'Hopital's rule, growth, and dominance. And so we're going to talk about what is L'Hopital's rule, what is an indeterminate form, and how can we use L'Hopital's rule to compute limits of indeterminate form. So we're going back to limits going towards as x approaches 0 and as x approaches infinity. And we're going to talk about, different methods of computing these limits, different than, we've learned before. Then we're going to talk about what dominance is between a group of functions, and then we're going to talk about how we can determine dominance with by using L'Hopital's rule. All right, so let's go ahead and get started. Moving some stuff around here so I don't unplug a wire. All right. Okay. So let's suppose we want to calculate a limit as x goes to 0 of e to the 2x minus 1 over x. So the first instinct is to just plug in 0 for x. Okay? So if we do that, we get e to the 2 times 0 minus 1 over 0. And so e to the 0 is 1, 1 minus 1 is 0, and we end up getting 0 over 0, which is not good. So when this happens, in previous sections in the beginning of the semester, we looked to see if there was anything we could factor out. If x was going towards infinity, we tried dividing everything by the highest power term. But here, we can't really do either of those things. So what are we to do? Well, we're going to be talking about something called L'Hopital's rule. And basically, all that means is if you plug in your limit and it looks like this, or it looks like this, what you can do is you can take the derivative of the numerator and the denominator and plug in your x, whatever x is approaching, and that's going to be your limit, okay? So let's kind of see what this means graphically a little bit. So the whole idea here is we are using linear functions to approximate, functions that are not linear. So for example, e to the 2x minus 1 is not a linear function. But, since we're approaching 0, this is really the only part of the function we care about. And if you were to zoom in really, really close to e to the 2x minus 1 near x equals 0, what you would find is that it would approximately look like the line y equals 2x. It would look very, very close to that the more that you zoomed in. And why is that? Well, if you were to find the slope of that tangent line, you would just take the derivative of e to the 2x minus 1, plug in 0, you would end up getting a slope of 2. And, finding the actual equation of the line would involve plugging in, x and y into your y equals mx plus b form. And the point of me saying all of this is that, that tangent line to the curve looks very, very close to the curve at x equals 0, the more you zoom in. And so what we're going to do is we're going to just approximate e to the 2x minus 1 by using 2x instead, because it looks so close to it when you zoom into x equals 0. So this problem now becomes this. And so what we are looking at is the ratio between 2x and x, these two lines, as x goes to 0. And we can see that, we have a removable discontinuity here, and so our answer here is just 2. Now, another thing you could do is you could plug in x values before canceling that are very, very close to x equals 0, and it's still going to give you an answer of 2. So the point is that if we use a linear approximation, then all we have to do is look at the ratio of the slopes, okay? And this is kind of, where L'Hopital's rule is coming from. All right, so let's do some practical examples here. So the first thing we need to define is what is an indeterminate form. Basically, if you have 0 over 0 or infinity over infinity. So the first one we look at is 0 over 0. And basically that's just saying, if you have a limit as x goes to some a and you plug in, and if f of x goes to 0, if your numerator goes to 0 and your denominator go to 0 as x goes to a, then we have 0 over 0 and the limit may or may not exist. Now, we've seen this before in the beginning of the semester. So, for example, this is what we did. This was the, what we did before. So, we plugged in 1 first, because x is approaching 1. That's like our a value. Plug it into the numerator and the denominator, and we have an indeterminate form because we get 0 over 0. All right. Since we have that, we need to figure out something else. So what we did was we saw if we could factor something and divide out a removable discontinuity. So in this case, we can factor out an x out of the numerator. And we get this. And on the bottom, we have a difference of squares. So that can be factored like this. And now we have a nice, we can divide out those x minus 1 factors. And from here, we can just plug in 1 for x. So we get the limit as x goes to 1 is 1 over 1 plus 1, which is just 1 over 2. So that was the old way that we did this. Now, sometimes the old way is not going to work with these rational functions. Like, for instance, this guy. We can't factor anything out, so how are we going to deal with it? Well, what we can do is we can use L'Hopital's rule, and that basically says take the derivative of the top and the bottom, plug in what x is approaching, and then get your answer that way. All right. So let me just show you in practice what this means. Okay, so this is the L'Hopital rule. I know it kind of looks like the hospital, but it's L'Hopital, French mathematician. So what we're going to do is we're just going to take the derivative of the numerator. So the derivative of the numerator is 2x minus 1. The derivative of the denominator is just 2x. And now we're going to plug in 1 for x, right? Because that's what x is approaching. So this is going to give us 2 times 1 minus 1 over 2 times 1. So that's just going to, again, give us 1 over 2. So L'Hopital's rule. Now, you can only use L'Hopital's rule if when you initially plug in your, whatever x is approaching, you get 0 over 0 or infinity over infinity. Otherwise, you can't use this little shortcut. So let's do some more examples. Okay, so this is the second indeterminate form. If we plug in our limit and we get infinity, or if we plug in our a value into our variables and we get infinity over infinity, or negative infinity over negative infinity, or positive over negative infinity. Any variation of infinity over infinity, we can use L'Hopital's rule with. All right, so let's look at the old way we dealt with these. So the old way when we had x going towards infinity was we divided the numerator and the denominator by the highest power term. In this case, our highest power term is x squared. So we would do x squared over x squared minus 1 over x squared, all divided by 2x squared over x squared plus 1 over x squared. And again, we are going towards infinity here. So this is going to give us, well, let's see. So this is going to give us 1 right here. So we have 1 minus, now as x goes to infinity here, the denominator is going to blow up, and thus this term is going to go to 0. So we have 1 minus 0 over, well, on the bottom, these x squareds cancel, and I'm just left with 2 plus, again, this goes to 0. So I'm left with 1 over 2 as my answer. All right, so that was the old way. Now the new way, since initially, if I plug in infinity in for x, okay, so let's just start over. So let's do the new way, or L'Hopital's rule. If I plug in infinity in for x, I get this. So infinity squared minus 1, so this is infinity. This is going to give us infinity over infinity, right? The top is getting arbitrarily large, and the bottom is also getting arbitrarily large. So because we have this form, we can use L'Hopital's rule. And we have to have this form to use this. If we don't, then we can't use it. So L'Hopital says take the derivative of the numerator and the denominator. All right. So let's see. What is the derivative of x squared minus 1? That's just 2x using the power rule. And on the bottom, we have 4x. Now these x's cancel out, and we're just left with 1 over 2 using L'Hopital's rule. So you see we get the same answer. So this is just a new way of evaluating limits because, like I said, this is not always going to work, and the factoring isn't always going to work. So this is kind of just another tool in our toolbox to evaluate limits. So this was our first example. We wanted to take the limit as x goes to 0 of e to the 2x minus 1 over x. And I have been mentioning this L'Hopital's rule, and this is what it is formally. Basically, you take the limit of a quotient of functions, and if you plug in a and you get 0 over 0, or you plug in a and get infinity over infinity, then you can take the derivative of the top and the derivative of the bottom. And once you do that, you can plug in a and evaluate. Now, you can also, if you keep, let's say you take the derivative and you still get infinity over infinity or 0 over 0 after that, you can do it again. So you can use L'Hopital's rule more than once to evaluate these limits. Okay, so let's go ahead and do this one. So first of all, the first thing we need to do every time, don't skip this step, is to check. Check to see if we have an indeterminate form. Which is either 0 over 0 or infinity over infinity. If you don't have either of these, you need to stop because then L'Hopital's rule does not apply. All right. So the first thing we're going to do is we're going to, let me see if let's see. Oh, I do it on the next slide. Okay, so let's go ahead and just move over here because this is the one that we were looking at. So let's first check that. Okay, so if I plug in 0, right, in for x, I get e to the 2 times 0 minus 1 over 0, which ends up giving me 0 over 0. So yes, this is indeterminate form since it's 0 over 0, which means I can use L'Hopital's rule. L'Hopital's rule tells me to take the derivative of the numerator and the denominator. Well, the derivative of e to the 2x is just 2 e to the 2x using the chain rule. Now the derivative of minus 1 is just 0, and the derivative of x is just 1, okay? So the next thing I need to do is plug in, what my limit is approaching after I take the derivative, okay? So then it's just 2 e to the 2 times 0. So that is just going to give us, well, e to the 0 is 1. 2 times 1 is going to give us 2, okay? As we saw in the first slide when we were looking at, when we did that linear approximation of e to the 2x minus 1. So that's our answer. Let's do the next one. So the first thing we need to do is check, can we use L'Hopital's rule? Well, the way that I check is I plug in 0 for x in the numerator and the denominator. And if it was 1 here, we would plug in 1 for x, Now, what I have, well, the cosine of 0 radians is 1. So what I have is 0 over 1. So I can't use L'Hopital's rule here. This is not an indeterminate form. So can't use L'Hopital's rule. Right? Because it's not 0 over 0 and it's not infinity over infinity. But luckily, we don't have any weird things that are going on. 0 over 1 just reduces to 0. So that's our answer here. We didn't have to use any kind of like factoring or any kind of weird thing. We just plugged in 0 and there were no problems and we got out 0. So there it is. Okay. Let's see. All right, let's look at the next one. So the first thing you always want to check to see, can I use L'Hopital's rule first? So I'm plugging in 1/2 anywhere I see an x. So I do 6 times 1/2 squared plus 5 times 1/2 minus 4 all over 4 times 1/2 squared plus 16 times 1/2 minus 9. Okay. What I end up getting on top, I get 6 over 4 plus 5 over 2 minus 8 over 2, all divided by 4 over 4 plus 8 minus 9. And that's going to give us 0 over 0. All right? So yes, we can use L'Hopital's rule because 0 over 0 is an indeterminate form. So L'Hopital's rule says take the derivative of the top and the bottom independently. So the derivative of the top is just, using the power rule, 12x plus 5. And on the bottom, if I take the derivative using the power rule, I get 8x plus 16. Okay, the next thing is I'm going to plug in 1/2 to see if we get a nice number that comes out of this. So, because that's what my limit's going to. So I do 12 times 1/2 plus 5 over 8 times 1/2 plus 16. And let's see, that's going to give me, I believe, 11 over 20. So that is my answer for number 4. That's the limit. And we were able to use L'Hopital's rule there. All right, let's look at number 5, trig. So first I need to check to see if I can actually use L'Hopital's rule. So I look at the top, cosine pi over 2. Then I do the bottom, 1 minus sine of pi over 2. Well, cosine of pi over 2 is just the x coordinate, or the x value at pi over 2, which is 0 on the unit circle. And then the sine of pi over 2 is 1. So yes, we do have an indeterminate form here. We can use L'Hopital's rule. So I'm going to erase some stuff so I have room. So L'Hopital's rule says take the derivative of the numerator and the denominator and see what happens from there. Okay, so the derivative of cosine, let's see, that's going to give us negative sine of x. Derivative of 1 is just 0. Derivative of minus sine, well, the derivative of sine is cosine, so the derivative of minus sine is minus cosine. And these negatives can cancel, and so I'm just left with the sine of x over the cosine of x. All right. Now what I want to do from here is I want to see if I plug in pi over 2, what my limit is going to be. So I'm plugging in pi over 2 here and there. So I got the sine of pi over 2 over the cosine of pi over 2. All right. And so what I end up getting on top is 1 and on bottom is 0. Okay. So this is not indeterminate form. Okay. 1 over 0 is not indeterminate form. So I can't use L'Hopital's rule again because of that. And so what I'm gathering here, since there's, nothing else to do and we have 0 in the denominator, we can say that the limit does not exist because we have that undefined denominator. Now, let's go ahead and, look at this on Desmos just to prove to ourselves that, yeah, this limit doesn't exist. So let's go ahead and punch this in Desmos. And let's see, we have, and by the way, sine over cosine is tangent, in case you guys remember that. So we have, actually, let's put in our original function. Our original function was cosine over 1 minus sine. Okay. I think I might have to get out of Desmos for a second. Let's see. All right. So we got cosine x all divided by 1 minus sine of x. And we're trying to see what happens when x goes to pi over 2. So I'm just going to put that in here so I can get a visual of where that is on my graph. Okay, so that's where x equals pi over 2 is that blue line. Okay, so this kind of, makes sense because what is the limit of this function as x approaches pi over 2 from the left? Well, it looks like as x is getting closer to pi over 2 from the left, y is going to positive infinity, right? From the other side, coming from the right, as x gets closer and closer to pi over 2, y is going to negative infinity. So the limit here does not exist, okay? One's going to positive infinity, one's going to negative infinity. All right. Let's do number 6. So the first thing we want to do is we want to check to see if we can use L'Hopital's rule. So we need to plug in our a into x. So we have infinity cubed over e to the infinity squared. All right. So the top is getting arbitrarily large as well as the bottom. So we have indeterminate form, which means we can use L'Hopital's rule. So L'Hopital's rule tells me to take the derivative of the top and the bottom independently. So the derivative of the top is just 3x squared. The derivative of the bottom using the chain rule, well, the derivative of x squared is 2x times e to the x squared. So that's the derivative of the bottom here. Now, let's see what happens if I plug in infinity here. Well, actually, before I do that, let's go ahead and simplify this. So I see an x that can cancel on bottom and top. And so I'm just left with 3x over 2e to the x squared. And I think that's as far as I can go. If I plug in infinity into the top, well, unfortunately, we still have 3 times infinity. And then, e to the infinity squared. I mean, the bottom is getting arbitrarily large, and so is the top. So again, we get infinity over infinity, which tells me that I can use L'Hopital's rule again, okay? So now I'm going to take this and use, since we got infinity over infinity, let's use L'Hopital's rule again. right? So what do we start with? We are starting with this guy this time after we took the first derivative. Okay, so let's go ahead and take the derivative of this guy, and we end up getting 3 on the top. On the bottom, we end up getting 4x e to the x squared using the chain rule. And again, I took the derivative of that inner function, which is 2x, multiplied it by that to give me 4x, times the derivative of the outer function, which is just e to the x squared, chain rule. Okay, so if I plug in infinity, well, let's see. I get 3 over 4 times infinity times e to the infinity squared, okay? So, you know, the bottom is getting huge, arbitrarily huge, while the top is staying at 3. So we end up getting something like 3 over infinity. And, you know, if we have a constant numerator and a bottom that's getting huge, this whole thing, this fraction is going to 0. So that's my answer here, 0. Now we could go in Desmos, and I'm going to write this as a note. Use Desmos to verify. So you guys can do this. What was the function we started with? We started with this one. See what happens as x goes to infinity. Is it true that y is going to 0 for that original function that we started out with? And you'll see that, yes, that is the case. At least I hope it's the case. Okay, let's carry on. All right, so let's go ahead and test to see if we can use L'Hopital's rule here. We are going to infinity, so what we have is ln root infinity all over infinity squared. Okay, so, you know, as the argument of the top gets arbitrarily large, you know, the top just gets huge as well. Infinity squared, clearly that's getting arbitrarily big as well. And so, yes, we can use L'Hopital's rule here. We have indeterminate form infinity over infinity. So L'Hopital's rule is telling me to take the derivative of the top and the derivative of the bottom independently. Well, what's the derivative of ln of square root of x? We have to use a chain rule here. So the derivative of ln of x is just 1 over x, right? So the derivative of ln of root x is 1 over root x times the derivative of that inner function, which is just root x. Well, the derivative of root x is 1/2 x to the negative 1/2. So that's the derivative of the top. The derivative of the bottom using the power rule is just 2x. And let's see if I can simplify this before I plug in my infinity. All right, so let's see. Well, on the top, I have 1 over root x. And then this x to the negative 1/2 is just, you know, 1 over root x. So, like, I can write the top like that. So that is the top rewritten. And then I can multiply straight across to give me 1 over these guys. When I multiply them, just go to x. So I get 1 over 2x, all over 2x, my original denominator. Okay, and then to simplify even more, I keep the top times the reciprocal of the bottom to give me 1 over 4x. And there's really nothing more I can do here. Now, what was I plugging in? I was plugging in x going to infinity. So I end up getting 1 over 4 times infinity. So 1 over a huge number is going to converge to 0. So that's my answer there, is 0 for that one. And again, I really encourage you to plug these original functions into Desmos. See what y is going to as x gets huge and see if 0 matches up with that. All right. Okay. So let's do this one last example, and then I think I'm going to take a break. Let's see. Okay. All right. So this time x is going to 0. So the first thing I'm going to do is I'm going to see, can I actually use L'Hopital's rule here? Do I have an indeterminate form? Well, if I plug in 0 in for x, anywhere I see an x, I get this over 0 minus sine of 0. So simplifying the top, I get anything to the 0 is 1. So I get 1 minus 0 over the sine of 0 is 0. So yeah, I do get indeterminate form at the end. I get 0 over 0, so I can use L'Hopital's rule. So L'Hopital's rule tells me take the derivative of the top and the bottom. Well, let's look at the top first. I can do it term by term. The derivative of e to the x is simply e to the x. The derivative of e to the negative x is, simply, well, the derivative of negative x is negative 1 times e to the negative x, using the chain rule there. And the derivative of minus 2x is just minus 2. So that's the derivative of the top. Now the derivative of the bottom is just 1. Derivative of sine is cosine, so this is just 1 minus cosine x. Okay? Let's go ahead and simplify before I plug in 0. So simplifying this, I get e to the x. These guys make a positive e to the negative x minus 2. Okay, let's see. So let's see what I get here. On the bottom, I get, I can't really simplify the bottom, but that's where I'm at. Let's go ahead and plug in 0 now to see what happens. So we get e to the 0 plus e to the minus 0 minus 2 over 1 minus cosine of 0. Well, e to the 0 is 1. E to the minus 0 is the same thing as e to the 0. So that's also 1. And then cosine of 0 on the bottom goes to 1. Okay, so now we have another indeterminate form. 2 minus 2 is 0 over 0. So now we need to use L'Hopital's rule again from, this derivative that we got. So let's do it. So taking the derivative of this thing, let's do this in green. So using L'Hopital's rule, again, e to the x, derivative of that is just e to the x. Derivative of e to the minus x is minus e to the minus x. Those plus and minus makes a minus here. And the derivative of constant is just 0. So, bye. That's good. Okay. Derivative of 1 is 0. Derivative of cosine is minus sine. So the derivative of minus cosine is just regular sine. So that's the derivative of the bottom there. Now let's go ahead and plug in our x equals 0. We get e to 0 minus e to minus 0 over sine of 0. And oh my gosh, here we go again. Man, this is annoying, right? 1 minus 1 over 0 equals 0 over 0. We need to use L'Hopital's rule again. Oh my gosh, here we go. Let's do it again. Hopefully it'll end one day. So L'Hopital's rule. Let's do it in caps because this is getting ridiculous. Okay, so now we take the derivative of, this guy, right? Top and bottom. Derivative of e to the x is e to the x. Derivative of e to the minus x is minus 1 times e to the minus x. Uh-oh, I think we're actually going to get somewhere. Thank God. Derivative of sine is cosine. Simplifying this, we get e to the x, positive e to the minus x. And, oh wait, I meant to put cosine here. Did I? Derivative sine is cosine? Oh, okay. Yeah. We did that already. We already took the derivative. I'm confusing myself. Okay. Okay, so, alright. I think we finally got this, y'all. Now, let's plug in 0. Anywhere we see an x, get e to the 0 plus e to the minus 0 over cosine of 0. And thank God, on the top, I can't even go down anymore. That's how ridiculous this is. On the top, we have 1 plus 1. On the bottom, cosine of 0 is 1. Therefore, our final answer, oh my gosh, is 2. Let's put this thing in Desmos to actually check that it is 2. Wait, this thing, our original function. And I'm going to let you guys do that because, well, actually, whatever. We'll do it. Let me write this down first. I just want to make sure you guys know how to check this. E to the minus x minus 2x over x minus sine, and we're going as x goes to 0. All right, let's put this in Desmos. That was a lot of work, but I think you guys are going to like this section better than the related rates and optimization. I just have a feeling. Okay, let's see. So we're doing e to the x, all right, minus e to the minus x minus 2x. And this is all divided by x minus sine x. So that was our function. And we're concerned with, as x goes to 0. That was our original problem. So when x goes to 0, we can see here's our function. As x goes to 0, well, it looks like y is going to 2. And that's what we got. So, good job, team. All right. There it is. All right, let's see. All right, guys, I'm going to go ahead and take a break. I hope this video was helpful. I'll see you guys in the next part. Thanks for watching. Hey, guys, let's go ahead and do these examples. All right, so number 9, picking back up on where we left off, we're trying to see if we can use L'Hopital's rule, because sometimes we're given rational functions that aren't easy / impossible to factor. So the first thing we need to do is we need to do our check before we even move forward. We need to see if L'Hopital's rule will apply. In other words, if we have 0 over 0 or infinity over infinity. Well, if I plug in, so we're going to 0 in this case, so if I plug in 0 for x, I get the following. So let's see. I'm going to get, on the top, I get 0 times 1 is 0, and on the bottom, I get 1 minus 1 is 0. So yes, we can use L'Hopital's rule here. Now, L'Hopital's rule tells me that I can differentiate the top and the bottom independently of each other. So if I differentiate the numerator here, I need to use the product rule because I have a function x times another function 3 to the x. So let's do the product rule. All right, so the product rule says keep the first times the derivative of the second. Well, the derivative of 3 to the x is one of those special derivatives, right? If you have a constant to the x, it's just going to be ln of that constant times your original exponential function. All right, so that's our special derivative. All right, so keep the first times the derivative of the second plus keep the second now times the derivative of x, which is the first. Okay, so derivative of x is just 1. All right, so that's the top. Now the bottom, So again, you know, if I differentiate 3 to the x, that's just ln of 3 times 3 to the x, and the derivative of minus 1 is just 0. All right, so this is what I have so far using L'Hopital's rule. So now what I'm going to do is I'm going to plug in 0 and see if that gives me a nice, numerical answer here. Well, I'm not going to waste my precious brain space, because what I see automatically is that if I plug in 0 for x, all of this stuff is attached by multiplication. So this is all going to go to 0 when I multiply 0 times that stuff. All right. Then if I plug in 0 here, I get 3 to the 0 over ln of 3 times 3 to the 0. Well, 3 to the 0 on top gives me 1, and on bottom as well. And so whatever ln of 3 is, so let's get an approximation for this. Just putting it in my calculator here, 1 over ln of 3. And I get approximately 0.910 is my limit here. Okay? All right, so I'm going to move on to number 10. So first thing, can we use L'Hopital's rule? Let's check. It's the very first step you want to take. Because if you don't get 0 over 0 or infinity over infinity, you need to go another route to evaluate the limit. All right. So let's go ahead and do this. We have ln of infinity over 2 over infinity. Oops. All right. So this thing is getting arbitrarily large, right? Because ln is the same thing as log base e. E to the what is infinity. You know, this is getting arbitrarily large, and then we square that. Same thing with the bottom. And so, yes, we have infinity over infinity here, and we can use L'Hopital's rule. So L'Hopital's rule says we need to take the derivative of the numerator and the denominator. So what's the derivative of ln x squared? Well, we need to use the chain rule because we have a function within a function. Our outer function is x squared. So the derivative of the outer, we just bring that 2 to the front. 2 minus 1 is 1, so that's the derivative of the outer times the derivative of the inner function. Well, the derivative of ln of x is just 1 over x, right? And then divided by the derivative of x, well, that's just 1. Now let's go ahead and clean this thing up. Let's clean it up. So if I clean it up, I just get 2 times ln x over x. That's basically everything simplified as much as I can do. Okay. So let's see. All right, so that's simplified. Now what I want to do is I want to go ahead and put my infinity in here and see if I get a numerical answer. So if I input infinity here, I get 2 times ln infinity over infinity. Now the top is getting arbitrarily large, so I have infinity on top, infinity on bottom, which tells me I need to use L'Hopital's rule again, okay, with this function. All right, so L'Hopital's rule, if I take the derivative of the top, which is 2 ln of x, well, the derivative of ln of x is just 1 over x, so that's the derivative of the top, and the derivative of x is simply 1, and so what that ends up giving me is 2 over x. Now, if I go ahead and put infinity in there, this is nice because I get 2 over infinity. When the bottom gets huge and the top stays constant, that converges to 0. All right, so that's my answer there. My limit is going to be 0 for that particular rational function for number 10. All right, let's go ahead and do number 11. Let me go ahead and make some room here. erase this stuff. All right. Okay, so first thing we need to check to see if we can actually use L'Hopital's rule. So we're plugging in pi for x and seeing if we get an indeterminate form. So what do we have? We have sine of pi over 1 minus cosine of pi. So the sine of pi is 0. And we have 1 minus the cosine of pi is negative 1. So this is going to give me 0 over 2, which is just 0. So L'Hopital's rule is not necessary here and wouldn't work anyway because we have 0 over 2, not 0 over 0, or infinity over infinity. So our answer here is 0. All right. Let's go ahead and look at this guy. So let's go ahead and plug in 0 and see if we have an indeterminate form to work with. Tan 0 minus 0 over 0 cubed. Well, the tangent of 0, remember, tangent is y over x. So if you look on your unit circle at 0 radians, y is going to be 0 and x is going to be 1. So 0 over 1 is 0. So tan 0 is the same thing as 0. So yeah, we have 0 over 0, which is good. So we can go ahead and differentiate using L'Hopital's rule. All right. So the derivative of tangent is a special derivative. It's 1 over x squared plus 1. So the derivative of tangent x is 1 over x squared plus 1. The derivative of minus x is just minus 1. So it's my top derivative. And on bottom, using the power rule, my derivative is just 3x squared. All right, now let me go ahead and plug in 0 in for my x's and see what happens. If I plug in 0 for my x, I get, I get 1 over 0 squared plus 1 minus 1 over 3 times 0 squared, which is 0. So, yeah, I get 1 minus 1. So I end up getting 0 over 0, which means I need to use L'Hopital's rule again. So let's go ahead and do that. So I need to take the derivative again of this quotient. So the way that I'm going to do that is I'm actually going to just kind of block this part off. I'm going to write this so that I can use the chain rule. I'm going to write it as x squared plus 1 to the minus 1. All right, so I haven't taken any derivatives yet. I just rewrote that fraction. And now I'm going to take the derivative of the top and bottom. So the derivative of the top, using the chain rule, is negative 1 x squared plus 1 to the negative 2. That's the derivative of the outside, times the derivative of the inside, which is just 2x, the derivative of x squared plus 1. Now the derivative of minus 1 is just 0, so that goes away. And on the bottom, the derivative of that guy is 6x. So now I'm going to go ahead and simplify as much as I can before I put my 0 in for x. So the first thing I notice is that these x's can be divided out. 2 goes into itself once, it goes into 6 3 times. And so what this really becomes is negative 1/3 times, well, actually, maybe we can write it like this. This, to the negative 2, we can stick it in the denominator and make the exponent positive. So let's do that just to see what's happening here. So this is that. All right, and so what I'm going to do now is I am going to stick in, let's see. I'm going to stick in 0 for x. And what do I get? When I put 0 in for x, I get negative 1 over 3 times 0 squared plus 1 squared. And so what I end up getting is negative 1 over 3. All right. Now let's go ahead and do the next one. Let's go ahead and do the next one. All right, we have secant minus tan. Let's go ahead and get rid of this. Okay. All right, so the first thing that you should notice is that we don't have a rational function. So we don't have like variables in the denominator. And to use L'Hopital's rule, you do need that, right? And so let's go ahead and kind of like force the denominator in here by rewriting these trig functions using identities. So from trig, if you remember this, secant of x, there was this thing called a reciprocal identity. Secant of x is 1 over cosine of x. This is a reciprocal identity. And then the tangent of x, if you remember, was is sine of x over cosine of x. And this is a quotient identity. All right. So that's what I'm going to do to kind of see if we can work a denominator in here. So instead of secant, I'm putting 1 over cosine of x. That's good. Denominator. Minus, instead of tan, I'm writing sine over cosine. And now this is good news because I happen to have the denominator cosine. Right, so I can write it like this. I can say, what is the limit as x goes to pi over 2 of 1 minus sine all over cosine? All right, so now I have a rational function, variable in the numerator and denominator. So let's see if L'Hopital's rule applies first before I start differentiating. Okay, so I'm plugging in pi over 2 into my argument. So I have sine, or into x, if you like that. 1 minus sine of pi over 2 over cosine of pi over 2. Well, on top, we just get 1 minus 1. On bottom, cosine of pi over 2 is 0. So yeah, we do have an indeterminate form of 0 over 0. So L'Hopital's rule does apply here. All right, so let's go ahead and take the derivative of 1 minus sine. Derivative of sine is cosine. Derivative of minus sine is just minus cosine. All right, so we have minus cosine on top. And the derivative of cosine is minus sine. Those negatives can cancel. And so we just have the limit as x goes to pi over 2 of cosine over sine. All right, so so let's go ahead and plug in pi over 2 in for x and see what happens there. So the cosine of pi over 2 is 0. The sine of pi over 2 is 1. 0 divided by anything is just 0, except for 0. All right, so there it is. All right. So this is a famous limit used to define E. I think they have this one in your book as well, in your Wiley textbook. So there's a little trick to this, okay? So what we're going to do is, the problem here is that we have this weird exponent, this variable in the exponent. And typically to get rid of that, because, we can't possibly write this as it is as a, as a rational function. So the trick to getting rid of exponents is logs, right? Because they're inverse operations, logs and exponentials. So what I'm going to do, and also what your book does, we'll just go through this, is I'm going to say let y equal 1 plus 1 over x to the x. All right, so that's the trick here. Now what we're going to do is we're going to take the ln, which is log base e, of both sides of this equation. All right. Now, one property of logs that you learned in maybe college algebra is that if you're taking the log of something with an exponent, you can pull that exponent back, like up to the front, basically, so that the exponent is being multiplied. So that's where this little trick comes in handy, because we wanted to get rid of that exponent to make this look a little bit simpler, and so we can just bring it to the front, and this is just a property of logarithms, why we can do that. All right, so from here, we are going to do a little bit of manipulation, because we still don't have a division, right? Like, we still can't check with L'Hopital's rule whether or not we can use, we can't check to see if we can use L'Hopital's rule quite yet. However, I'm going to do a little trick, okay? Instead of saying this is multiplication by x, I'm going to say equivalently that this is division by 1 over x, right? I'm just going to say, well, this is the same thing as dividing by 1 over x, right? So division is just multiplication by the reciprocal. So same exact thing. Now I have a rational function here. And so what I'm going to do is I'm going to take the limit as x goes to infinity, of both sides, right? Maybe I should have left more room. Let's do this. And this is where I'm going to apply L'Hopital's rule. So I'm going to plug in infinity anywhere I see an x, right? Because that's what, x is approaching. Now on the left, nothing is really happening because we don't even have an x variable to worry about. But on the right, well, what is happening as I plug in infinity? I have ln of 1 plus 1 over infinity over 1 over infinity. So, of course, the bottom 1 over infinity is going to 0. Now, this thing is going to 0, which means that this thing is going to 1. ln of 1, that's just going to be 0, okay? So, yeah, we have indeterminate form here. We can use L'Hopital's rule. So, let's go ahead and get rid of this. And we're just going to write this. And now what I'm going to do is I'm going to differentiate the top and the bottom by using L'Hopital's rule. So the numerator is, using the chain rule, is 1 over 1 plus 1 over x times the derivative of the inside. So the derivative of ln is just 1 over that argument times, well, what's the derivative of 1 plus 1 over x? Derivative of 1 is 0. The derivative of 1 over x is negative x to negative 2. All right, so that's the derivative of the numerator. The derivative of the denominator is negative x to negative 2. And these guys are going to divide out nicely. All right. Now, what happens? So, okay, let's rewrite what we have. We have limit as x goes to infinity of ln of y equals limit as x goes to infinity of 1 over 1 plus 1 over x. All right. So here we go. As x gets huge, what's happening to this fraction? Well, as x gets huge, this goes to 0. And so the limit as x goes to infinity of 1 over 1 plus 1 over x is just going to 1. Okay? So I can just replace that right side with 1. Okay, and remember that ln of something is the same thing as log base e. All right. So basically this is saying log base e of y equals 1. And this limit as x goes to infinity is kind of irrelevant here. But basically what it's saying right here, using properties of logs, is that e to the 1 equals y, or simply y equals e. Okay? So y equals e, and therefore, we defined this guy as y, and so therefore the limit as x goes to infinity of 1 plus 1 over x to the x is just the limit as x goes to infinity of e, and so we just have e. Okay, so that's one way that we can define e. All right. Okay, I'm going to go ahead and stop this video, and I'll see you guys in the next one. Thanks for watching. Hey guys, this is a continuation of this week's lecture on L'Hopital's rule. So I need to address the fact that I made a mistake on number 12. So I assumed that the derivative of tangent was 1 over x squared plus 1, which is not true. The derivative of tangent of x is secant squared of x. All right. So let's try this again. Okay. So yeah, we already established that for this one we can use L'Hopital's rule if we plug in 0 into this. So we're good. So now we need to take the derivative of the numerator and the denominator. Now, as I just mentioned, the derivative of tangent is secant squared. So we have secant squared of x minus 1 over 3x squared. Okay, so I'm going to use to just make this simpler, I'm going to use a Pythagorean identity here. So the Pythagorean identity is that tan squared, let's do x in this case. So tan squared of x is equal to secant squared of x minus 1. You probably learned this last year in trig. So that's what I'm going to do. I'm going to replace that before I go any further. All right. Now what I'm going to do is I'm going to plug in 0, and again, I'm going to get this indeterminate form, 0 over 0. So I'm going to use L'Hopital's rule again. Now, when I take the derivative of tangent squared, well, I'm just going to use the chain rule here. So the derivative of tangent squared is the same thing as, I can write it like that, right? So when I take the derivative, this is just going to be 2 tan of x times the derivative of the inside, which is secant squared of x, all over the derivative of the bottom, which is going to be 6x. Now, before I go on, I'm going to reduce this to 1 over 3x. And what I'm going to do from here before I take the derivative again, because again, if I plug in 0, I'm going to get 0 over 0. So I need to keep using L'Hopital's rule until I get something, that's not of indeterminate form. So what I'm going to do is, again, I'm going to use this Pythagorean identity. So if I look at this guy and I isolate secant squared, well, this is just secant squared of x equals tan squared of x plus 1. So that's what I'm going to put this in here before I differentiate. So this is just tan x using the Pythagorean identity again. I get tan squared x plus 1 to replace secant squared all over 3x. That way I'm just in terms of tangent, and this makes it a little bit of an easier problem. All right, so let's see. If I distribute this guy in here, I get tan to the third x plus tan x all over 3x. Let's go ahead and take the derivative here. So the derivative of tan 3x is going to be 3 tan x squared times secant squared using the chain rule plus secant squared, that's the derivative of this tan x, all over 3. All right, now if I plug in 0 at this point, this guy goes to 0. Tangent of 0 is just 0. The secant, let's see. Right, and this also goes to 0. 0 times the number is 0. The secant squared of 0, well, secant is, r over x. And at 0, x is 1, r is 1 on the unit circle, so this just goes to 1. This is 1 squared is 1, and so our answer here should be positive 1 over 3 versus the negative 1 over 3 that I gave in the last part of this lecture. All right, so now that we've cleared that up, let's get back to our problem of dominance. All right, so let's talk about what is dominance. Well, dominance is just basically one function growing faster than the other. That's what dominance is. And a fact that I'm not going to prove here, but a fact is that exponential functions dominate or grow faster polynomials all the time. So if you ever have an exponential versus a polynomial, the exponential is always going to dominate. Okay. So with that being said, let's go ahead and look at this definition. So it says, all right, for positive functions f and g, we say that g dominates f as x gets huge, as x goes to infinity, if the limit as x goes to infinity of the quotient is 0. Now, what does that mean? Okay, what does that mean? So g is dominating, right? G is growing much, much faster than f. And that's why this limit makes sense, because as x gets huge, so does g. G gets a lot bigger faster than f, and so this denominator is going to be huge while this stays not as huge. And so that's going to eventually converge onto 0. And what we can do is we can use L'Hopital's rule to prove dominance easily. All right, so we want to prove that the function x to the 1/2 dominates ln of x as x goes to infinity. Well, what we're going to check is that the limit, what we're checking here, is we're checking that the limit as x goes to infinity. Now, what's dominating this guy? So it's our denominator. We want to prove that this is equal to 0. That's what we want to prove. And we're going to use L'Hopital's rule to do it. So L'Hopital's rule says if we plug in infinity here, well, we end up getting infinity over infinity, right? Ln of infinity over infinity to the 1/2 is indeterminate form. So we can use L'Hopital's rule, which says, let's take the derivative of the top. Derivative of ln of x is 1 over x, over the derivative of the bottom, which is 1/2 x to the negative 1/2. And before I plug in before I plug in infinity into this, I'm going to simplify to make it, clean it up a little bit. So on top, I have 1 over x. On bottom, I'm going to clean this up by saying this is the same thing as 1 over 2 square root of x, right? This is the same thing as x to the 1/2. So that's what we're doing here. Now, to simplify this, I keep the top times the reciprocal of the bottom. All right, maybe I'm running out of room here. So multiplying straight across, I get 2 root x over x. And remember, if I'm going to actually change this back to 2x to the 1/2 over x to the 1. And remember, if I have the same base and I'm dividing, I keep the base and I subtract the exponents. So 1/2 minus 1 is negative 1/2. And so that just leaves me with 2 over the square root of x, basically. So what happens as x goes to infinity? Well, I have 2 over something huge, right? Basically, I have 2 over infinity. And so this is going to go to 0. So that is my answer here. So yes, it turned out that this limit was 0. And so that proves that x to the 1/2 dominates ln of x. In other words, x to the 1/2 grows faster than ln of x. Okay, so let's do another example. Which function dominates? X to the 5th or x to the 7th? So here we have 2 polynomial functions, and when you have 2 polynomials, the one with the highest power is going to dominate. That's a fact. Let's prove it. All right, so how are we going to prove it? We're going to prove that the limit as x goes to infinity of x to the 5th over 0.1 x to the 7th is equal to 0. That's what we want to prove. That's going to show us that this guy is growing faster than the top, right? And eventually it's growing so fast that the top can't catch up, and so it's going to converge to 0. All right. So let's go ahead and prove this, and we're going to use L'Hopital's rule, because clearly if we plug in infinity in here, we're going to get indeterminate form. So we can use L'Hopital's rule. And doing that, I differentiate the top and the bottom. And I'm going to go ahead and simplify this before I plug in anything. So this is going to simplify to 5 over 0.7 x to the second power. Okay. Now if I plug in infinity in for x, well, I just get 5 over infinity. That converges to 0. So we have just proved that x to the 7th dominates x to the 5th, because that the limit of this quotient x to the 5th over 0.1 x to the 7th as x goes to infinity is 0. Right? The bottom is growing much faster than the top. That's what's happening there. All right, let's do one more example. I think it's one more, yeah. Which function dominates as x goes to infinity? We have x to the 10th versus e to the 0.1x. Now, again, this is a fact that the exponential, the variable in the exponent is going to dominate. That's a fact, because this is a polynomial. And this is an exponential function. So let's prove that. So we're proving that the limit as x goes to infinity over x to the 10th over e to the 0.1x is equal to 0. All right, so we can use L'Hopital's rule because, clearly we have infinity over infinity if we plug in infinity in for x. So let's go ahead and differentiate the top and the bottom using the chain rule. I have 0.1 e to the 0.1x. Well, this is still going to give me infinity over infinity. So we have to use L'Hopital's rule again, and I think you guys can see where we're going with this. So this is still infinity over infinity. And instead of, doing this 7 more times, we need to pick up on the pattern here, okay? Well, what's happening to the bottom? The bottom is always going to infinity, right? It's getting very big. We're just using the chain rule over and over again, right? And this exponent is staying there. And so the bottom, no matter how many times we differentiate, is still going to have that x in the exponent. And so it's going to infinity. But the top, once we differentiate a bunch more times, we're going to have a constant number up top. And we're going to have, something. This is very informal. I'm writing this. We're going to have something e to the 0.1x. That's what's happening here. That's the pattern. So the constant number, we have a constant over something huge, right? This is going to be something huge when we plug infinity in. And so this is going to 0 at the end of the day. We have a number over something huge. That's going to 0. And so, this is very like hand wavy, but yeah, we've proved that e to the 0.1x is going to dominate x to the 10th. Now, you should try it the other way. If you flip this to see, what if you said, oh, well, I think x to the 10th dominates. Well, you could flip this and then you would see that, no, in fact, it doesn't, right? Because you're going to end up getting, infinity over a constant at the end of the day. And that's not the same thing as 0, a constant over infinity. So, anywho, that was my lecture this week. I hope you guys learned something, and I'll see you guys next week. Thanks for watching.